Hello, maurieo. We're going to have a bit of a look at graphs of trig functions. The trig functions that we are all so familiar with, the sine, cosine and tangent, are some of the best known periodic functions. They repeat themselves. I say, they repeat themselves. Yes, they repeat themselves. Now if we have a look here at the sine graph in blue, we can see that it repeats itself. And as it turns out, it repeats itself every 2 pi or 360 degrees. It has a period of 2 pi. And the graph itself, they just range from 1 to -1. That's known as, or we call that, the amplitude. It has an amplitude of 1. The cosine graph's pretty much the same, shown here in red. Period 2 pi, amplitude 1. It's just moved a little bit further along than the sine graph, but it repeats itself. The tan graph, however, is slightly different in that it has these asymptotes. These are lines that the graph gets very close to but never actually touches. By investigating what happens either side of them, we can sort of see where they occur. Generally, these asymptotes occur on your calculator where you might go, for instance, sine of 90 and it'll show up as infinity or perhaps some sort of irregularity. And these are what occur at the exact values of these asymptotes. Now when we talk about pi radians, that's the equivalent of 180 degrees. 2 pi radians, 360 degrees. This is just another way of measuring angles. And I've shown here a little table showing the relationship between pi radians and degrees. Pi by 12 radians is 15 degrees, and we can work on those increments all the way from 0 to 180, and then again through to 2 pi if you wish. So that's a handy little table there so that you can relate the various angles in radians and degrees. One of the things we like to do with graphs is to sketch them. Sometimes it's not always that easy, but there is one basic thing that we can always fall back on, and that's our table of values. So if we take here, for instance, the secant graph, remembering that the secant of x is 1 over cos x, we can create a table of values, say between 0 and 2 pi, as I've done here, and then we can work out the value of the secant just with our calculator, or perhaps some of the native cunning that we may have for the values that we know. Some of these will look quite familiar to you, these numbers, as you see them. And then it's just a simple matter of plotting up the values, the degrees along here, and the range up and down here, the y values, and then just joining the dots. However, we do have a few problems here at 90 where we can see that we get the infinity symbol there I've put, or whatever you get on your graph, on your calculator. This is where you need to do a little bit of investigation, see what's happening either side. So we can see here, if we look at secant 89 degrees, that the graph is getting quite large as it gets closer to 90, large and positive. So we can see that then there must be some sort of asymptote there. If we also look at secant 91, we can see that the graph is getting, as it moves away, or as it moves away from 90, it's getting smaller and negative, but it was very large and negative as it's getting between 91 and 90. So that tells us that there's an asymptote there in that graph, and there you are with our table of values. Very easily done, that we can plot our graph. And here it is, this trigonometric graph here of the secant. Looks like it follows in the tradition of all the others, and that it repeats itself. Mathematicians like to compartmentalize things and have like what we call a general equation. That's one that applies in a lot of different situations by using different variables. Now the trigonometrical graphs, they have general equations in this form here, where y equals a sine bx plus c plus d, and y equals a cos bx plus c plus d. And these sort of in a general terms, and I've written this up here, relate to translation of the waveform y equals a sine bx and y equals a cos bx. I say translations because that moves the graphs up and down or left to right. I perhaps more correctly could say transformations, because some of the things actually make the graph skinnier or move them together, change the scale and change the sort of period of the graph depending on these various coefficients A, B, C and D. So let's have a look at that. A gives us the amplitude of the graph, which we know is the size of the wave. B gives us the frequency, how many oscillations take place. And C is the phase angle, or the left or right shift, how much it's shifting left or right. D is the constant offset, and that allows us to raise or lower the graph, which is in effect a true translation in the Cartesian plane. There are a couple of other things associated with our trigonometrical graphs. The period t, which is equal to 2 pi over b, and that is how often the graph repeats itself, the period, which that's quite handy to know. And the phase shift, which equals negative c over b, and that is the displacement of the wave form. So let's have a look at a bit of an example here as how we might use this general equation. Let's say, for instance, we want to find a, b and c in this function y equals a sine bx plus c, where the period t of the graph is pi by 2. So using our little formula and information there, we know that t equals 2 pi over b. In this case, that's equal to pi by 2. So just multiplying that out, or cross multiplying as some people refer to it, we get b pi equals 2 times 2 pi, 4 pi, so b is equal to 4. So there we have it, we have b. Now the maximum value of y is 3 when x equals 0. So the maximum value, that tells us straight away what the amplitude is. Because the sine graph and the cosine graph only range between 1 and negative 1, that the maximum value being 3 tells us immediately that a is 3. Now we also know that a, b and c are positive, and that c is less than 2 pi. So that tells us from our information, using some of the other information above, that when the maximum value is 3 when x is 0, so we can put 0 into the graph and immediately that tells us that bx would be 0. So we can say y equals 3 sine 0 plus c, and that equals 3. Now we can see that there's a 3 on both sides, so if we divide through both sides by 3, we get sine c equals 1. Now we know that when the sine of 90 or pi by 2 is equal to 1, we can write that in mathematical terms, sine to the negative 1 c equals pi by 2. So that can tell us straight away that c is equal to pi by 2. And so there, now we're in a position to be able to write out the graph with all the coefficients in place, and we can see that y equals 3 sine 4x plus pi by 2 is the equation for the graph. So sine to the negative 1 of c is pi by 2 tells us, of course, that c equals pi by 2. So there we have it, some information. Given those little bits of information, we can work out the equation of that particular graph. For the equation y equals cos 3x plus 2, let's have a look at this and see if we can find out what is the range. Now, because we have our general equation of the graph y equals a sine bx plus c plus d, we are able to straight away see that a, the amplitude, in this instance would be 4. So the range of the graph would be negative 4 less than or equal to y less than or equal to 4. What is the period? Well, we have an equation for the period. T equals 2 pi over b. And looking at our general equation and our familiarity with it, we can see straight away that b is 3. So the period of this graph would be 2 pi over 3. Or, if we look back to our earlier table, 120 degrees. What is the phase shift? Well, again, we have a formula for the phase shift. It's equal to negative c over b. Again, from our general equation, we can see that c is 2 and b is 3. So therefore, the phase shift in this instance must be negative 2 over 3, negative 2/3. Let's not forget that's in radians. Okay, so now moving along, we want to use our skills in our general equations to sketch the graph y equals a half sine 2x plus 1. Referring back to the general equation y equals a sine bx plus c plus d, straight away we can see that a equals 1/2, b equals 2, c equals 0 in this case, looking at it very carefully, and d is equal to 1. So our period t is 2 pi over b, 2 pi over 2 in this instance, or pi. C equals 0. Therefore, there is no translation in the x direction. D equals 1. Therefore, there is 1 unit translation in y. So, let's have a look at our graph. First of all, we just plot up our graph y equals a half sine 2x, and then we just move it up 1 unit to give us y equals a half sine 2x plus 1, or our 1 unit translation in the y direction. I notice that I've left the y off my little notes here, so I'm just going to add that in now so that we can get our notes up to date. So here we go, adding the y. So d equals 1, which gives us our translation in the y direction. And there we are, we have our graph sketched. Note that a sketch is a sketch. It's not an extremely accurate depiction of the graph. It's just a sketch with all of the important features highlighted. So there we have it. The amplitude of our graph in this instance here is a half, as we can see. So we've with the translation of 1, it is moved up and sort of ranges between 1.5 and a half, there being no negative values in this instance. Now, just to remind you once again that a sketch is not equal to accurate, it's just a sketch of the graph. Now here we have the sort of major calculation that we need to do in this sort of unit that we're looking at, and it's, as you can see, it's getting quite complicated. So we have two waves that are colliding, and the formula for the waves is ax, or a of x, equals a wave A 4 sine 2x, and wave B as a function of x is 2 cos x plus pi over 2. So that one of the best things that we can do with these waves, of course, is to plot them and see how they come out. Now, one way of plotting them, there's a number of ways available to you. You could use an Excel spreadsheet if you have skills in that area, or you could use the little GeoBra, which is a little free online program that will plot the graphs for you quite easily. So first thing we need to do is to write down the combined waveform. So that's just we add the two together. So C of x, the combined waveform, would be 4 sine 2x plus 2 cos x plus pi by 2. And you can see on the diagram there that I've actually plotted the two graphs, and I've also plotted the combined waveform, which is where the two get added together. And this can be done by just adding them together and seeing what happens at each instance. So sketch the two graphs, and we use the general form of the graph. We can see for graph 1 that a equals 4, b equals 2, c equals 0, d equals 0. So using our graph sketching skills, we're able to scratch that. Then graph 2, we can see that a equals 2, b equals 1, c pi by 2, and d equals 0. So again, we can sketch that. Step 3, we add the coordinates of the two waves to plot the combined wave form, which I've shown here in a sketch form here. Now, the fourth thing we need to do is describe the major troughs and peaks in the combined wave form. A trough will occur when you draw these very accurately, either using Excel or possibly GeoBra. Describe the major troughs and peaks in the combined wave form, and a trough will occur at 0.7 pi in this case, and a peak at 1.2 pi. Explaining what this means in real terms, the waves will reinforce and create a bigger wave. So that is what the diagram shows. So plotting these graphs, don't forget that you can always plot these manually using a table of values. There's another number of options open to you, but the best thing to do is to certainly plot a copy of the graph so that you can get a fairly good picture of what the combined waveform would look like. There you go, and good luck with all of that.